my name is KSteinacker, and I'm going to be talking now about the power management system, particularly about the power management system taking an AC signal and turning it into a DC output. And we're going to be talking about, particularly in that, some of the circuits that are involved with that, a bridge rectifier, an RC filter. We're going to be talking about the some of the semiconductor physics behind the diode. We're going to be talking about electrostatics inside of that, and just the general circuit design.
So we'll start with the rectifier. So the diode bridge here is what causes this input voltage to be turned into a rectified positive output. So we have this plus minus Vrec here. In the case, we have positive on top, negative on bottom. And so you're going to have a current flow induced here. And so whenever Vn is, well, we can look at it ideally first. Let's look at ideal. So, and also an ideal case. Assume ideal diodes. So when Vn is greater than 0, and you'll have current flow through them. So you'll have current flow through diode 1, and then that's going to have case. We have the negative at the top here. And so these are both going to be off. So if Vn is less than 0, you're going to have the diode 2 and diode 3 are going to be on. Positively biased here. And we have an output here, also going to be a positive output. And it will return. Let's take a look at this. So to be linear, our input would have to be both homogeneous, have homogeneity, and it also have to have additivity. Now, let's just try a negative scaling first. So if we scale the input by -1, we'd have this. This is negative Vn. And so as you can see, it is opposite at every point. Scaling it by -1, you get a different input. But if you scale -1 input, you're also supposed to get a negative at the output, but you still have this positive waveform yielded with a negative input. When we add these two together, if we add these two waveforms, this Vn1 and Vn2, you're going to get a Vn3, and that sum of that is going to be 0. If you add these two together, you're actually going to get, if you add them, your output's going to be a positive amplitude of 2V0. So you see that both the properties of homogeneity and additivity do not hold up. It's not a linear system. And now, as promised, we'll be talking a little about semiconductor physics and how it relates to electrostatics. And I have drawn here a graph of charge density. And in order to find the electric field inside, we have this big Gaussian surface. It's going to go all the way through here. It's going to go all the way outside on the opposite side. We know that E field equals 0 here. And that's where we get our bounds. Our electric field is going to follow this path here as we integrate the negative side. And then if we integrate the positive side, it's going to go back up here. So that's going to be the electric field graph with respect to the x-axis. Voltage, or this is where we're going to find VD on here. This is going to be the voltage, this x graph here. And that is simply, we find the voltage is equal to integral of electric field dx. So we have Ex here, and so we can just integrate that. Whenever you integrate a linear function, you're going to get a quadratic not here, V naught negative V naught. We know that the voltage across the diode, VD on, is going to equal to V naught. And now, to try to wrap everything up, we're going to conclude with A few words about the RC circuit we haven't talked about at all, and tying it all into the rectifier and VIN, VREC, VOUT, and talking about how the whole system works. And so again, we have this sinusoidal input. It goes through the diode, and we have our rectified output shown here. Instead of this very noisy, very jumpy from 0 to V on, we want to have a very smooth ripple. And how we accomplish that is with this capacitor. It's going to discharge through R2 here. I already have some Kirchhoff voltage law loop equations written down here. We have V out does equal VC. We have on this side we have the V rectifier equals V in minus 2 VD on. We'll talk about that again. And then V out equals V rec minus IR1. And so let's try and draw the output here. So again, V rec rectifies whenever 2 VD on the in value is met. That goes here. So that comes on and it's rectified and just for that purpose. And then we'll talk about V out. So V out, we're going to have like a charging capacitor here. And then whenever V out equals that little gap right here, that's value IR1, whatever the current value is, IR1. Whenever they meet, then the diodes are turning off at that point right here. Then the diodes turn off and the capacitor discharges. And so our V out discharges to the next line here. And then it comes up and it discharges, comes up and it discharges. And so we get a nice ripple DC with much smaller voltage drop.
Thank you for watching my presentation on the power management system. Hopefully it was helpful and well done, and stay tuned for the next KI presentation.